Hi, ladies and gentlemen. Today we are going to talk about modern physics, which is a lot of stuff covered after 1900 and really focuses on our changing understanding of the nature of light itself and how that has now led to what we call today quantum theory. For the longest time, light was believed to be a wave, rightfully so, because as an electromagnetic wave, it was a combination of an electric field and a magnetic field. They were able to measure its wavelength and amplitude. The gamma rays, of course, have a higher frequency. Radio waves have the lowest frequency and the longest wavelength. And right in between, in a tiny, tiny narrow band, literally 1% of the entire spectrum, is our understanding of what visible light is. Violet being the highest frequency and red being the lowest frequency. So whenever we talk about our wavelength of visible light ranging from 400 nanometers to 750 nanometers, if I had asked you to correspond what are the corresponding frequencies, we could always use our old wave formulas. V is equal to F lambda. So the frequency for 400 nanometer light, now that's the shortest wavelength, the highest frequency, so this is going to be violet. 750 nanometers is a longer wavelength, shorter frequency, so this is going to be our red. So the frequency would equal to the speed of light divided by the wavelength in, of course, meters. Okay, so having done that, we're able to solve for the frequency to be 7.5 times 10 to the 14th hertz. Light was understood to be a wave for many reasons. Most of course, being the fact that they could undergo diffraction, the spreading of a wave around the barrier. They could undergo interference, in that when two waves hit each other, the amplitudes combine, whether they become larger or they cancel out to become smaller. A particle couldn't do that. And the fact that it could undergo polarization. So these three experiments prove that light has to be a wave. But what we're going to talk about today is the particle nature of light. How light can possibly act as both as a particle and a wave, like a wavicle. It was Max Planck who first noticed something interesting with what we call black body radiation. He noticed that when things were heated, and superheated I mean, they start to glow. And the hotter they become, the color changes. In fact, if you look at lava, the yellowish parts of lava are much hotter than the reddish parts of lava. In fact, the hotter and hotter something becomes, the frequency changes. Now, this didn't quite make sense, because if something was being heated up, he had assumed that with the increase in energy, there would be a corresponding increase in the amplitude of light as a wave, meaning that it would become brighter and brighter and brighter. It wouldn't change colors. It would just stay red and just get redder and redder. It's brighter and brighter. But this didn't happen. Instead, what happened was, as the energy increased, the frequency of light increased as well. Now, this didn't make any sense to Max Planck, and he just stated it that energy was based on frequency as a mathematical error of some sort. No one really questioned him at the time because no one really understood what was going on. But Einstein took this idea. You see, there was this other phenomenon that was recently noticed called the photoelectric effect. Photo meaning light, electric meaning electricity, meaning when light hits something, hits a certain type of substance, electrons come off, which is really the birth of solar power as we know it today. Now, Einstein had a few issues with the photoelectric effect. The main issue being that, well, as light strikes the surface, electrons are knocked off, meaning that light strikes the surface, electrons literally jump off and they complete the circuit. They create electricity. Now, you see, Einstein's problem with this was that the photoelectric effect only worked with certain colors. When blue struck the substance, electron was knocked off. But when red would strike the substance, nothing happened. And this stumped people for a very long time. Now, going back to Max Planck, because Einstein looked at Max Planck's formula. He saw Max Planck had written this formula. E, the energy, is equal to H times F. E is, of course, energy, which is going to be measured in either joules or electron volts. Max Planck had simply graphed the different energy levels that were observed with the corresponding frequencies of light, and he noticed that as energy was increased, the frequencies would increase as well. And he took the slope of this and just gave it a constant value. So we call this Planck's constant today. Okay. Now, Planck's constant has two values based on whether we're going to use it in joules or electron volts. So it's either 6.63 times 10 to the negative 34 joule seconds, or 4.14 times 10 to the negative 15 electron volt seconds. Okay. So we're going to use this formula more in a moment, but I also want to show you a variation of this formula, which is very common. Because V is equal to F lambda, I know that F is equal to V over lambda. So if we're talking about light, it would really equal to C over lambda. So this formula can also be HC over lambda. Now, since H is a constant and C is a constant, we actually have on our reference table the value of HC. .99 times 10 to the negative 25th joules meters, or 1240 electron volt nanometers. Okay, so let's actually do a quick practice question with this formula before we move on to talk more about the photoelectric effect. In this example question over here, we're given the energy of a photon of blue light, the wavelength being 450 nanometers. So if I wanted to calculate the energy of that, E of this photon, which we'll talk more about later on, is equal to HC over lambda. So it would equal to 1240 electron volt nanometers. Notice my constant is given to us in nanometers already, divided by 450 nanometers, which equals to 2.76 electron volts. If I didn't want it in electron volts, I could always convert it back to joules. Knowing that 1 electron volt is 1.6 times 10 to the negative 19 joules, I end up with 4.41 times 10 to the negative 19 joules. Okay? So that's just a quick practice with using this formula itself. One of the biggest confusing aspects of the photoelectric effect was that light was, since it's believed to be a wave, under the wave theory, the energy of light should have been directly proportional to its amplitude, or in other words, its brightness. So if we take a look at this model of the photoelectric effect over here, we have a lamp shining on a sodium surface. And when you increase the brightness of the lamp, okay, you can see it's getting brighter and brighter and brighter, and nothing's coming out. No matter how bright you make this lamp, no matter how much supposed energy we're putting in, it wasn't working, and scientists were baffled. But if you simply change the frequency instead, to change the color, instead of red, orange, yellow, blue, nothing's happening yet, but eventually you reach a point with green, all of a sudden electrons are coming out. Even if you make the light as dim as possible, okay, even if you make it as dim as possible, electrons still came out. I mean, not many came out, but they still came out. If you increase the intensity of this light, made it brighter and brighter and brighter, more electrons came out. So they're confused. What exactly was happening over here? Why was the brightness correlated only with the number of electrons coming out, not whether they came out in the first place? And when they increased the brightness, when they increased the frequency even more, they noticed all of a sudden those electrons are coming out with a much higher kinetic energy than before. They come out with a much higher average velocity. And the higher and higher you go, the faster it went. If you decrease the intensity, all you would decrease were the number of electrons coming out. It had nothing to do with whether or not the electrons got knocked out in the first place. So Einstein took this idea, and he realized, what if light wasn't a wave? What if it was also a particle? You see, the particle model works pretty well, because under the particle model, the energy, so if this is wrong, the energy isn't related to the brightness. The energy is directly related to the frequency, just like Max Planck had said. What you have are billions of little particles, what we call photons, which are a particle of light. These photons have both particle properties and wave properties. Mainly because of the fact that they have no mass. These particles were made out of pure energy. Which gave them the ability to act like a wave also, because when 2 points of energy meet, they can interfere, they can combine, but then they pass right through each other because there's no mass whatsoever. So the brightness, by increasing brightness more and more, what you're really increasing is equal to the number of photons that are being shot out. So if you look at this animation over here, it helps us to understand what's going on. Light is a particle, a single particle that goes into the molecule and collides with it. It gets absorbed, the energy gets absorbed, and it knocks the electron out. Over here, just to recap again one more time, okay? Understand that the energy of the photon is directly related to its frequency, and that the brightness of light is equal to the number of photons coming out. So if you make these assumptions, then everything that's happening in the photoelectric effect, it makes perfect sense. Okay? If I decrease the frequency, the electrons that are being knocked out have less speed, less kinetic energy as they're coming out. If I increase the intensity, I'm shooting more individual photons in. It's like I'm throwing more balls into it and knocking more electrons to come out. In fact, if I graph it over here, okay, watch how in, let's see, this bottom graph over here, as you increase the frequency, you increase how much energy those individual photons have on average. Okay? But notice there's a point down here, okay, where if it falls below that frequency, nothing comes out. If I move the bar down now the other way, once I go below that frequency, nothing comes out anymore. That point is what we call the threshold frequency. In other words, the minimum frequency to knock an electron out. Okay? And that threshold frequency is different for every substance. For sodium right now, we can see the threshold frequency is around about 565, well, that's the wavelength. That would be around 0.6 times 10 to the 15th hertz. Of course, there would be a threshold wavelength as well. Okay, if you talk about threshold wavelength, okay, you can see as you have more energy, the wavelength is getting smaller and smaller. As you have less energy, the wavelength is getting larger and larger. Okay, so vice versa, we have something called the threshold wavelength, which is basically the maximum wavelength to knock an electron out, because wavelength is inversely related with energy. If I look at my second graph over here, current versus light intensity. So let's say I have a certain number. So if I decrease the intensity, you can see that the current, which is really the electrons coming out, decreases down to 0. But as I increase the intensity, I'm shooting more photons in and knocking more electrons out, and a direct relationship. But notice, intensity has no effect on the individual energy of the photoelectron itself, of the photon itself. That can only be affected by changing the frequency. So I'll make a note here. Intensity has no effect on the frequency or slash energy of the photon. Okay, it's only equal to the number of photons that are present. Okay, so if I were to, we could just redraw a graph now over here. The kinetic energy of the electrons, which is given to them by the photons of themselves, starts with some sort of threshold frequency, F naught. We already defined that to be the minimum frequency needed to knock an electron out, and it ends up being a direct relationship. Once they're knocked out, the more energy you give to the photon to give to the electron, the faster it goes. And notice the slope over here, since it's still energy versus frequency, is still equal to Planck's constant. There's absolutely no relationship between the intensity of light versus the maximum kinetic energy, because intensity is just the number of photons that are being shot in. And by shooting more photons, all you're really doing is knocking out more electrons. Okay? So otherwise, there's no relationship, and these graphs are important to understand. Here's a real-life demonstration of the photoelectric effect. In this case over here, they're just charging some metal strips with a positive charge. Okay? And with a positive charge, you can see them repelling each other. But now they're using an ultraviolet light and shining it on the aluminum can, which pushes out a whole bunch of electrons and cancels out that charge. And that's why the foil strips just close right back up.